Okay, in the third segment, we want to actually look at how we will calculate the various values we need, the values of slope, as a function of position down the mountain. So essentially what we're going to do is try to follow a route that the Lamar would take down the mountain and then use that to calculate at each spot to calculate the slope. So again, looking at the general pattern, we start up here at the top. We eventually want to get down to here, and what we want to do is figure out values of slope at various locations along the route that can go into our determination of slope versus distance. So to do that, we'll want to look in specific detail at different spots along the path. We'll start near the top. Now the slope is going to change rapidly near the top and slowly. So in this area it'll change. In this area it'll change rapidly. Down here it will change more slowly. So we're going to want to get points closer together near the top, maybe fairly often. But as we get down into the flats, we can have our points where we're determining slope further apart. Now before we go into that, just a reminder of what slope is and how we're going to calculate it. Now remember, when we have a line or the side of a mountain and we want to decide what the slope is equal to the change in height over the change in distance. That is, we oftentimes call it rise over run. And so in this case, the slope, if this is our situation, this is the rise, this is the run, and so we would look at the change in this height. So let me call that the y, and we would call this the distance, we'll call that x. So the slope will equal y over x. Pretty straightforward and something that I know you've seen before. Now to determine this on the volcano, what we're going to do is actually go at different positions down to get our x value, and then we will use changes in elevation to get the y. So from this we will use change in elevation. Okay, so with that in mind, let's go on and actually think about the type of values we're going to need to get. So we're going to have a picture like this. We have the actual topographic map shown here. The top of the mountain is here, is the red pin. The town of Ording is there. And the path we can look at, we have several paths as we've talked about before, but in this example we're going to follow the path from the top down through here, and that follows along the Carbon River and eventually makes it to Orton. So to do that, we're going to want to initially start at the top, start measuring distances from the top. Now the path is curved, so we're going to approximate that path by following line segments. So we might go like that, and then like that, and then like that, and then like that, and then like that, and then. So we're going to do it by a series of line segments rather than trying to do it in one fell swoop. And so we're going to need to work our way, starting here, and then we go to a point there, connect those two up, then maybe go to a point here, connect those two up, and we would get a slope at this point, a slope at that point, a slope at that point, along that segment, etc., and work our way down. Now the other thing we're going to want to think about is the fact that the slope represents the average slope along this entire segment. So when we go around to plotting it, we would typically plot that slope at the midpoint of that line segment, or this section at its midpoint there. So we're going to also want to be calculating not only the length from one spot to the other to get the slope, but where the midpoints are on our different line segments. So all of these are things we'll want to keep track on in a in a table or something like that. Now to do all this, we're going to use the app that's topo maps that are on the iPads, and so we'll go over that in class on the details of using it. But it has some tools in it that we can use that will be very helpful. Now to look at the type table we want to make, here's the table that we can work from. I'll provide you a copy of it. It's got the various things that we're going to care about. There's going to be the distance from the previous point. Remember, we're working our way down the volcano in line segments. But in terms of plotting it, we have to know where we are in terms of total distance. So that's what I'm calling cumulative distance. That's measured from the summit. The distance change, that will be the distance over which we're measuring the slope for each of these points. That will be in meters. This midpoint distance is going to be the distance from the top of the mountain to the midpoint of the position we want, because that's actually going to be where we want to plot it. And then the elevation change will be the change in elevation from the start of the line segment to the bottom of the line segment. And with having that, knowing the elevation change and the distance change, we can then determine the slope. Once we have the slope and the midpoint distance, we can then take the natural log of the midpoint distance, and that's going to be that one there, and the natural log of the slope, and then we will have the values to put in those, and this would be what we would actually end up plotting. So let's look at what this might look like in the real case. So we'll start at the top of the mountain. Here I've zoomed in, and we're going to want to follow a route that maybe starts at the top, and we're going to want to get over to here. Excuse me. So we're going to follow a path that might go from here, then to there, and then down. So up at the top, we may have to follow a little bit of a circuit to get to the main river channel, but this would be the route perhaps that it would most likely take. But it also means that, some things at the top may be a little more complicated. So if we start at the top, we want to measure a distance, and the first thing we have is a tool, this tool up here, which allows us to measure distances from a point. So if I turn that tool on at the same plot, we now have this. So we have circumferences 2, 4, 6, 8 kilometers. And it also is telling me the position of the center, which is where the two crosshairs come together. And the elevation of that is at 4,358 meters. So that's my starting elevation, and I'll use that as I calculate an elevation change. Now my first point is going to be, I'm going to want to get to somewhere over here. So if I physically move within the app to get to that point, and now I'm at that location there. That's now at the crosshairs. Up here, I'm given the distance from the starting point to the end point. That's 3,559 meters. Or that's the elevation, excuse me, 3,559 meters. The distance from there to there is 2.83 kilometers. And so now I have a change in elevation from my previous value, which was 4,358. And over here, I'm now at 3,559. So I have a change in elevation here of about, this comes out to be 799 meters, and 799 meters over 2.83 kilometers. So I can do that calculation, 799 divided by 2,834, and that gives me a value of the slope of about 0.283. So that now is the slope of this first line segment. I now repeat that step. I move my starting point to here and do the same down to the next point. So I'm now going from here to here. I now have a change in elevation that will be based on the elevation at the new point, which is 2,241. And remember, the elevation at the Previous point was 3,559 minus 2,241. So that's going to equal an elevation change of 1318 meters. We're going to do that over 2.38 kilometers, or we have a slope equal slope is going to equal 1,318 meters divided by 2,384 meters, and the slope now is 0.55. Now, this should strike us perhaps as a little odd. This slope is actually larger than the slope before, and we said that our volcano should have the slope being steepest at the top and then work its way down. That's the hypothetical volcano. Our real volcano will be a little different from this, but when we plot these out and then fit the best line to it, these variations amongst the true line will come out and we'll still come up with a good situation. So we can just keep following this along, follow from that point to the next. We now have 1,600 meters of elevation change over about 4 kilometers. We do the same calculation. We now put our center at that point, move our way down the model to another place. We now have 840 meters elevation here. We can do the elevation change from there to there over about 5 kilometers. And we just keep working our way down the volcano as we go. And we tend to be making our points further apart as we move further down the volcano. So with all that, we then can come up with the values that we need to fill in this table. At each one of those points, we have a distance from the previous point, we have a cumulative distance, we have a distance change that we're using in calculating our slope. Most of the time, this and this, in the examples I just showed, these are the same, but there may be times when you actually are doing it on a more fine details. This midpoint distance is the sort of cumulative distance plus half of that from the top down. That's so that we plot in the right place. We get an elevation change from one location to the next. We calculate a slope by taking the distance from the previous point or the distance change that we're using and the elevation change. So these two come together to make the slope. And then once we have those, we can easily take the natural logs. So that's what I want you to do. And as the homework assignment, before we come to class on Wednesday, I'd like you to actually take the maps that you're given in class and start to fill out this sort of a table, working your way down from the top of the volcano. And you can use this tutorial as an example.